here you go.
Okay, so the talk is about the dynamics of PKS equation. So I will do it a little bit quick. So I will just introduce four parts, and the first one is tell you what the equation is, and the second one is introduce some existing results, and then I will give you only one insight about the long-term dynamics of the solution to the PKS equation. And finally, I will introduce my results. Due to the time limits, I will omit all the proofs, okay, in the paper. Okay, so basically the PKS equation is in its simplest formulation is given by this kind of diffusion aggregation equation, right? So this is the this is used basically in the chemotaxis theory, and this is a basic fundamental model for describing the cell populations, right? So this is a very baby version of the models. Okay, so basically there are a lot of generalizations of these models, and how to solve this kind of problem, because you see there is a Poisson equation there. So if your solution U has enough integrability, then you can just use the convolution of U with the fundamental solution to represent the solution V, and then you plug into the V to get the non-local equation of this kind of type, right? So this is a non-local equation, and so this is the equation. But to understand this equation is a little bit tricky in higher dimensional case and the 2D case. The reason is in the high D case, you just need enough integrability, then you can define this quantity. And after you define this quantity, you take a gradient and do the convolution, or you do the convolution first and take a gradient. They are basically the same thing. So in the high D case, this equation can also be written as gradient En convolute with U without any problem. But this kind of situation is different in the 2D. The reason is in the 2D, this kind of convolution is finite if and only if the multiplication of U with the fundamental solution is integrable exterior to a disk. So in the 2D case, the enough integrability of the solution U cannot guarantee the integrability of the functions here. So this is a very typical example. So you can see this U is basically L infinity, right? So you have enough integrability already. But after you multiply the log of R, immediately this function is not integrable. So in 2D case, this kind of two notations are different. So in 2D case, we can only use this kind of notation if you want to get a general solution, instead of using the gradient E2 convolute with U, because this guy is not defined in the general case. But there are many conditions so that you can use to still use this kind of formulation. For example, you can give like a finite free energy condition, or you can assume the finite second moment condition. So if you have some extra conditions, you can still use this kind of formulation. But in the most general formulation for the 2D case, this is the general one, okay? And historically, there are many existing results. So this is my second topic. So I will give you a quick review, okay? So in the 1980s, there are some results, okay, already, but these results based on the free energy, okay, finite free energy, finite second moment, and this kind of thing must be L1 integrable. So with these three conditions, then BDP, the Perton, Blanchard, and the Dubutte, they give a critical threshold for the PKS equation. Below the threshold, the solution exists globally, and beyond the threshold, the solution blow up, right? And basically, at the threshold, the situation is very tricky, okay? It's very delicate. So at the critical regime, solutions to the PKS equation basically can be proved to exist globally in time. So this can be done. But what is not clear is so this can be done, but even though the solution exists globally in time, their long-time behavior is still different within different scenarios. So the difference depends on the finiteness of the second moment. So the Masmoudi, Carrillo, and the Branche, they showed that if your solution initial data is concentrated enough in the sense that their second moment is finite, then as t goes to infinity, the solution will blow up. And the blow up is its convergence to a Dirac measure as time goes to infinity. So this is the first blow up rate for the critical threshold case, right? And then there also coexist non-blow up solutions. So the non-blow up solutions is obtained in 2012 by Branche, Carden, and Carrillo. They basically find out the proper dissipative weak solutions to the classical 2D pedelec characteristical equation. So as I said before, if your second moment is finite, the solution must blow up. So their solution must have infinite second moment. So that is the solution found by the Branche, Carden, and Carrillo. So both of the solution has finite free energy, but the Masmoudi's solution has finite second moment. And the Carrillo, Carden, and Branche's work, they have infinite second moment. Okay, but in this work, they didn't show any like a convergence rate, but they claim that the convergence rate problem can be studied in terms of the stability result of Gagliardo, Nihenberg, and Sobolev inequality. But they just claim that they are related, but they didn't show any convergence rate. And the convergence rate problem is finally completed by Carden and Figali 1 year later after their publication of the existence result in 2012. Okay, and in the subcritical regime, also, as I said before, the solution exists globally in time. And for the global solution, there are also two different results. The first result is by Branche, Dobut, and Bertin, based on the finiteness of free energy and the second moment. And the second result is due to Wei Dongyi, and basically he dropped all the assumptions. Okay, he dropped all the assumptions. He just need to assume the finiteness of the mass. And he showed that if the mass is below 8 pi, the solution exists globally in time. And if the solution, if the mass is beyond 8 pi, then the solution blows up. So no other extra assumptions. So this is a very beautiful result, I think, right, on the existence result. But the drawback of the Dongyi's paper is he just studied the L4/3 solution. So that means all the blow up criteria is just on the blow up of the L4/3 equation. Okay, so he didn't get any like a high integrability result on the blow up of the solution or the existence of the solution. So though the solution exists globally in time, still just in the L4/3 class, not in the classical class. Okay, at least in the paper. I don't know if he can show it or not. Okay. So this is for the 2D problem, and for the 3D problem, the results are quite few, okay? Almost no results in the 3D results. In the 3D case, even though the long-time dynamics or like the blow-up results, the results are quite few. So there are some well-posedness results. So the first local well-posedness result is given by Bieler, Kozono, Sugiyama, and Yahagi. Okay, so basically their initial data is in LP, and the P is bigger than the critical index here, n/2. And if you want to get a global solution, then you should some scaling invariant norm to be small. That is basically a standard argument. So the scaling property for the PKS equation is given by that. If you have a solution, then you do this scaling, it is still a solution. And then there are many scaling invariant spaces associated with this kind of scaling invariant. The first result is on the Ln/2 space. If you see this kind of scaling is basically invariant under the Ln/2 space, then the Sugiyama and the Yahagi and the Kozono and the Correa's, Bertin, the Zag, they showed basically that if the n/2 norm is small, then the solution globally exists. And then also extended by Kozono and Sugiyama, to the weak LN over 2 space initial data, okay, in the weak. And then there are a sort of other scaling invariant spaces. I just listed them and showing their embedding relationships. And then you can see on the right-hand side that this is the largest space, okay, the Basalt space. And indeed, this is the case. So it was in 2013, and the Mail and the real set, they basically showed that if any solution and if any like a Banach space of the tempered distribution set is invariant under the scaling, right? Under the scaling just shown, then it must be embedded into the homogeneous Basalt space. So in the Navier-Stokes equation, this is -1, and in the PKS equation, this is -2, right? So suppose if you want to study the long-time global solutions, then the largest space you should use is this kind of homogeneous Basalt space. And indeed, it is the case. And Lemaire and the real set in 2013, they basically showed that if the initial data is small in this space, and then the solution will exist globally in time. But similarly as the Navier-Stokes equation, which the result obtained by Bougain and Pavlovich in 2008, the solution obtained by Lemaire and the real set is also not well posed. Not well posed in the sense that they have no continuous dependence on the initial data. So even though your initial data could be very small in the Basalt space, but as time goes to infinity, your norm could become arbitrarily large. Okay, so this kind of eoposeness does not happen if you confine yourself in a little bit smaller class. That is the so-called Tribel Rizalkin space. So this is a very interesting result due to Iwabuchi and Nakara in 2013. And they basically show that if the initially the Tribel Rizalkin space norm is small, then in the future, the norm keeps to be small, right? So this is the result. And also this is our starting point to study the long-term dynamics of the solution obtained by Iwabuchi and Nakara under the smallness assumption of initial data given here. Basically, in this result, they just show the existence of global solution, but they didn't tell us any information on the long-time behavior of the solutions. So our work, part of our work, is just after this job. Okay. And there are also some blow-up informations, but these informations are really partial, okay, quite incomplete. So I just list some of the results here for your reference, but I won't go into too much details into here. But compared with the 2D case, the blow-up for PKS equation in higher dimensional case is known quite little, okay, not almost no results here, okay. So our result in the following are twofold. So the first one, if you remember, Dongyi proved the existence result, but he didn't drop the assumptions on the long-term dynamics. So up to before our work, in order to study the long-term behavior of the solutions, you still need the 3 assumptions there. So the first motivation for our work is to drop all the additional assumptions, even for the study of long-term dynamics, okay? And the second motivation for the work is to extend to study the long-term dynamics of global mild solution to the PKS equation in high D, after the work of Nakamura, okay? So before I show our work, our results, let me just give you a hint, okay, about some insight about the long-time dynamics. So the first insight is about the 2D case. That is why the people needs free energy assumption, okay? So if you have free energy, F to be finite, then you can have this dissipative relationship on the free energy. So the free energy is basically monotonely decreasing, right? Non-increasing. And then you can combine with the Hardy-Littlewood subgraph inequality. This is sharp. So you can see the difference here. The free energy has 1/4 pi. And in the Hardy-Littlewood inequality, you have coefficient 2/m. So if you combine the finiteness and the Hardy-Littlewood subgraph inequality, so finally what you can have is and estimate on the dissipation. So then you can just use the equation because we know Laplace V equals to the U, so you can do integration by part. So you can reduce from this estimate to this estimate. So you can see when m is less than a pi, this sign is positive. So in this regime, you can get the control on the Dirichlet energy of V for any time t. So the solution cannot blow up. So that is the major reason why almost all the work up to now relies on the assumption of finite free energy and the finite second moment. So they need all the quantities in the definition of free energy to be finite. So that's the reason. And for the higher dimensional case, we can still do the same thing, but I haven't seen any works up to now to use the free energy study the long-time dynamics. But if you write the free energy under the self-similar coordinate, you still have this kind of relationship on the free energy. So this H is free energy. You can see this is the entropy minus the M and the Dirichlet energy of the chemotrectant. So this is also true. So if this is true, then you can see you can use two inequalities. One is gross logarithm inequality. So the dissipation term here can bound this kind of entropy. So this is a very standard application of gross logarithm function. Then if you plug this guy into here, so you can just immediately see that the free energy satisfies this kind of inequality. So immediately you can find out the control on the free energy. So in the second step, you can also use César-Carl-Beck inequality. So the César-Carl-Beck inequality gives you a lower bound of the entropy here. So the lower bound of the entropy is basically given by the distance between the solution and the Gaussian under the L1 distance, right? So immediately you see that basically your solution will convergence to the Gaussian as time t goes to infinity. So this is a very quick result and a very cheap result, but this result has its drawbacks. It just controls the L1 distance. And it gives you the best decay rate is this one, e to the tau over 2. So this is the best information. And we want to also improve this information. Okay, so now I just introduce my results with Jiayou Xie, also in the Chinese U of Hong Kong. So our first result is on the 2D. So for the 2D, we drop all the assumptions. So you can see all the three conditions are equivalent. So the total mass is less than a pi in the subcritical regime directly implies the L infinity decay of the solution. And this L infinity decay 1 over t is optimal. You can never improve anymore. And then not just that, if you correct the solution by using the self-similar profile, then you can get even faster decay. So this decay is given here. And this is true for any p bigger than 1 and less than infinity. So both endpoints can be achieved. Okay, so this extended largely the results before, which only works, for example, on this space. Okay, so we extended it to include all the LP integrability from 1 to infinity and including the endpoints. Okay, so this is for 2D. And for the 3D and the higher dimensional case, I just said we continue the work of Nakamura. So we assume this assumption. So if you assume this assumption, then you can find out the 4 other equivalent conditions. So all these conditions are equivalent. So you assume this kind of smallness, then you can immediately imply the decay as before for the 2D case. And in the higher dimensional case, this decay can be improved to the optimal, t to the n over 2. And then if you minus the heat kernel, you can get this optimal decay as well. So this kind of information is also true for all p bigger than equals to 1 and less than or equals to infinity. So this is for the 3D case. And for the 3D case, if you want more detailed information on the long-time behavior, you can put a finiteness assumption on the second moment. So if you have finiteness assumption on the second moment, then your solution can be written out into higher order approximations. So now for n bigger than or equals to 5, this result is dedicated, it depends on the dimension. If your dimension is bigger than 5, then you can see the correction is fundamental solution and the center of the mass and the gradient. And then this is kept, and you can have extra 1/t decay here. So this extra 1/t decay is also optimal. You cannot improve anymore. So this is for dimension greater than 5. If dimension equals to 3, your correction you should have more corrections here. Except the usual one, you should have some more corrections from the system. And this W should be solved by this parabolic equation. And it can also be represented explicitly if you like. So this is for the 3D case. And for the 4D case, the correction is also different. So it's very tricky for 3D, 4D, and 5D and beyond. So for the 4D, you can see beyond this, besides this kind of approximation, you still need this kind of log T correction. So this is for the 4D, and all the coefficients can be explicitly computed out. Okay, so that's all.
Okay,
yes.
So thanks for the talk. Any questions from the audience? Or in the Q&A chat room? Okay, I have a question indeed. You have explained in terms of mathematical analysis why the m strictly smaller than a pi is important.
Mm-hmm.
So physically, actually, what happens when m beyond a pi or what?
I think physically the mass will be accumulated near some points. You mean the m bigger than a pi, right?
Right, exactly.
So then the mass will be accumulated. So the bacteria will be accumulated to some location, concentrated. Yeah.
You mean when the initial mass is
the density of the mass will become to be infinity.
Mm.
So you mean there's a blow up? I mean,
yeah, there will be a blow up. But the blow up profile is not so much satisfactory so far. So even though people only show like a 4/3 blow up or like a second moment blow up, but indeed it still has some space to improve. But anyway, the mass will blow up. Yeah.
I see. But the solution you're talking about is not relating to the eta pi, right?
Yeah.
Okay, and also, your solution in the small sense, it doesn't satisfy the energy law, wLogo rho, right?
You mean the free energy?
Yeah.
Actually, we are not using the free energy, so I'm not checking if the solution indeed satisfies it or not. Yeah, but it needs to control the behavior at infinity.
Yeah, in the infinity, when time goes to infinity, it's okay because the equilibrium automatically will satisfy the equation. But just for the time, finite time, or even in the time between 0 and infinity, because
we didn't check. Yeah, we didn't check.
So in your solution, there's no blow up, and even there's no mass concentration, or even in the two-dimensional case, you never consider the blow up or something.
No. That's only for the subcritical region.
Then in your sense, because in some sense, the equation or the nonlinearity is just the square function, right? Almost like a u squared.
Yes.
So maybe you can consider some general type of nonlinearity, and you got a way to the p power or something like that.
Yeah.
To a critical power, right?
Yeah, exactly. So this is just starting.
Okay.
Yeah.
Good.
Yeah.
Thank you.
Thank you.
So we have some more questions from the chat room. So the first question is, what is the physical meaning of free energy?
Oh, what's the physical meaning of free energy?
Yes.
I think I'm not quite familiar with. Anyhow, I only know that is log U is kind of entropy used in, but I'm not quite familiar with its physical background.
Okay, so there is another question from the chat room. Why is huge differences between
the difference
3, 4, 5?
I didn't show you all my slides, but I can show you one difference from the hint I have shown. So basically from here, so you can read from here the free energy equality. So in the free energy equality, there is a factor Fn squared. I'm not emphasizing on it, but if you see the Fn is this kind of thing, so this is e to the 1 minus n over 2 times the tau. So this quantity in different dimension will gives you different order of the error. So for example, if your n equals to 2, this is just finite. So it gives you nothing, right? But if your n equals to 3, then you have e to the minus tau over 2 term. So if you want to consider the higher order approximation up to this order, you have to involve this term in. But if you just consider the zeros order approximation, you can just drop it. And if your dimension n equals to 4, then you have e to the minus tau here. So if you consider the higher order approximation up to this order, but in 4D, so you can throw this term. But so that's the reason why we have different correction comes out. Yeah. But there are other tricky reasons because during the proof we discovered 2 different null conditions for the cancellation. And this kind of null conditions still help us to find out a different order of the approximation. So that's why 3D, 4D, and 5D have different correction there. So I just show you one simple evidence, but anyhow, okay.
Yeah, thanks.